Today we will go on to the last part of integration. So our lecture today would closes the topic of integration. And one thing I want you to recall from before is when you have a single variable integration, there's a lot of different skills of integration. But we only mention just one of the most important skills, and that is to do with a substitution. So if we have converted a double or triple integral into iterated integrals, then we are falling back on single variable integration techniques. But there are times when we want to use a higher order technique where you're not doing repeated single variable integrals. We will be dealing with a double integral head-on using substitution, or triple integral head-on using substitution. And the main arena that this happens is when you have a change of coordinates where an object is more naturally described in a different coordinate than the Cartesian rectangular coordinates. Oh, I did not open the meme, but here's my plan. So the plan today is we're going to be dealing with a topic that's usually called change of variables, but it's just the method of substitution. And in fact, like tricks up for 2D and 3D, etc., higher dimensions. So we'll deal with both polar, cylindrical, and spherical coordinates as examples. Okay, so, but by no means it is the only possible coordinate. There are other possible coordinates, but we will use the most useful ones. So let's begin. So the beginning of the change of variable has to deal with an example from 1D where we would bring this idea to 2D. So if you were going to integrate something like integral from 0 to 1 of x times square root of 1 minus x squared dx, this is in 1D. The way you might go about doing this is, well, you see the trouble of a square root, and for algebraic reasons, you want to substitute x as a function of u. In this case, this function of u would likely be chosen to be sine. Okay? And corresponding to x equals 1, you would choose u equals, okay, let me put them together. There are two values to choose. Corresponding to x equals 1, you might choose u to be power of 2, and for x equals 0, u will equal to 0. And also have to compute the change of the differential. So you have the dx will equal to cosine u du, and the integral becomes integral from u equals 0 to u equals power of 2, and then replace everything x to everything u, you get sine u, and then square root of 1 minus sine square u, and then dx, and then it's cosine u du, and so on. That will be a trigonometric integral that you can solve, which I don't solve here. I use this as an analogy. So our arena, our background, our situation is to treat double integrals, which would be integral over region D in R2 of function of x and y, and then you have dA, and also a triple integral over a region in R3, which we call E, a function of 3 variables, and dV, using the same idea. And for notational simplicity, I think I would start with 2D. So in 2D, a substitution would look like this. So if your x, instead of x as a function of u, you're going to have x as a function of u and v. And this is too big, smaller. And again, y, you would have it replaced by 2 variables. So this is a simultaneous which we call back substitution. So this is not the forward substitution that you use. It's like the tricks up. Tricks up is a kind of back substitution where you replace the letter by a function, and not by a function by another letter. So this is the change of variable we are concerned about in 2D. Then the theoretical result that comes out from it is that you have something called a Jacobian. So I'll cut the long story short and just tell you what happens when you have this. Now the key thing here is when you're doing this double integral, we're not worried about this part. Replacing x as a function of u and v and y as a function of u and v should be fine. That's not the hard part. The hard part is the element of integration. So here, the element of integration, in the past, we have the easier case, which is just dx dy or dy dx, depending which variable you integrate first. But now you will have a multiplier, and the multiplier has a special name. So the multiplier has this symbol, which you will see in the very last subsection of our textbook. We won't go too deep into that, but we want a formula for that for convenience. This multiplier is called the Jacobian. So just like the previous multiplier we've seen for optimization is named after Lagrange, this one is named after Jacob. Okay, so Jacobian, it is actually the matrix determinant of this, all these four partial derivatives. So once you decide on a change of variables, you can have this formula and just do partial differentiation, and you get four first order partial derivatives arranged in this manner. So the quick way to write it down is just this. Okay, so that's the Jacobian. And well, we won't do a general case. It's good to know at the back of your head that, okay, there is change of variables, and the change of variable brings about partial derivatives, which we arrange on a matrix and give you a determinant. What we want to know is the standard ones. So for example, so case in point, one of the standard way of making this change of variable is like trig-sub. But in two variables, we are not just substitute by sine or cosine or some trigonometric functions. We'll be substitute by both the radius and the angle. So in this case, x can be written as a function of r theta but using polar coordinates, and same for y. So this is the standard change of variables to convert the Cartesian coordinate system to polar. And once you change it to polar, you can calculate, for example, round x round r is cosine theta, and then round x round theta equals minus r sine theta, and round y round r is sine theta, and round y round theta is r cosine theta. And you'll be able to figure out, using the formula I gave above, that this change of variable will lead to the multiplier, which we call Jacobian, to have things cancel to give you exactly r. So that's the formula you need. This is the Jacobian for a polar coordinate change. So if you change the variables to change to the polar coordinate variables, this is the extra multiplier you need. So your dA, the key ingredient, I use red, is not just dr d theta now. There's an extra multiplier here, which is 1, coming from here. So with this, let us do a quick calculation. So the calculation that I want to do is about area. So the area of a polar curve. So that's the case where this is called for. So find the area bounded by the polar curve. And this polar curve is very simple equation. R equals cosine 4 theta. And I'm gonna get a picture from our textbook. This is the one. Okay, I've sketched something with less petals before, and this is from example 5.33. So this is situation. We want to find a shaded area. And so on. So I have 8 identical petals. Okay, with a sketch, it makes it much easier for us to know how to simplify our integral. So area, as before, is always defined by your domain of integration and then dA. This never changes with your coordinate system. Okay, so this is the initial formula for all kinds of area, no matter what coordinate system you use, some exotic or coordinate system you would use. This is the formula. So it's just 1 times dA. But what's changed now is that you can replace dA by just dx dy, and a more convenient one is to use the polar coordinates. And for the polar coordinates, you also need to figure out how you can express d in terms of it. So first, let's just use an English sentence to express how I'm going to simplify it. It is 8 times the area of the first petal. Okay, so look at the area of this first petal. Which one do we want to choose? We'll choose this as the first one, which is hitting at the positive x-axis. And this first petal would have your pi, if you do this, asymptote, it's a symmetric domain in terms of theta. You have this theta between minus pi over 8 and positive pi over 8. Okay, so it's half of pi over 4. Pi over 4 is here. Okay, so let's go back to the polar curve sketching. So this is a range of theta, and correspondingly, your r, of course, to measure your area, you want the points that's inside the petal. And to get the points inside the petal, your r should be greater than the boundary, less than the boundary, which would be your r cosine theta, 4 theta. Your cosine 4 theta, so there's no r here. Cosine 4 theta. And the lower bound will be 0. And this would give you your d, okay? So this here, area of the first petal, is 8 times the double integral over d, which is the range of theta value being from minus pi over 8 to pi over 8, and the range of r values between 0 and a cosine 4 theta. Okay, and so that's the first part. That resolves you this part using your new coordinates. The second part you need to resolve, not the integrand is the easy part. The second part you need to resolve is the dA. And the dA is going to be r dr d theta. Take it as a given. So once we've seen it once, memorize it. We don't derive it every time. So once you have this, this will convert into an iterate integral. So look at this. It's nice. These a, b, c, d's are constants. The limits of integration are constants. So we're back into our honeymoon in the very beginning, where we have the Fubini's theorem and we can integrate in whatever order you want. You can also split integrals when your integrand is a product of functions in one variable only. So this is exactly what we will do. So I'll just write an integral for r, so from 0 to cosine for theta, and then r, and then dr. And there's an outer integral, which is from minus pi over 8 to pi over 8 at d theta. And notice, I have to do it this way. I can't swap the order because here, it's not a constant. This guy, not a constant. I mix up my next example with this one. So this one, upper low limit, is not a constant. That's why I cannot mix up the order. Okay. So I have to do this with r integration first, because r depends on theta. Okay. So this integral is not hard to integrate. You get integral from minus pi over 8 to positive pi over 8, and the integrand is r squared over 2, and then substitute the upper limit to be cosine 4 theta, the lower limit is r equals 0, and d theta. Okay, let me add all these markers just so that we don't get confused. So this part is not hard to get. You get 8 times integral from power over 8, negative of that, to positive power over 8. And the new integrand is a half of cosine squared for theta, and then minus 0, and d theta. And the rest is trigonometric integral. The answer will be power over 2. So this is the first example. You can do something similar for other coordinate systems, like spherical coordinate systems, for finding areas and volumes and like that. So before we have found the volume of a unit ball, meaning a ball with a radius of a unit, which is 1. And that we use the standard Cartesian coordinates and require a few steps. Let us use a different coordinate system and make it way easier. So before we can do that, we need to write down the spherical coordinate system for which we'll do this transformation to make integrating really easier. So we have the x and y and z, and they are now no longer just functions of 2 variables. We're talking about 3 variables: rho, phi, and theta. Rho, phi, and theta. Z is rho, phi, and theta. So the last guy here is rho cosine phi, and the rest have the rho sine phi in front of it. And then you have this cosine theta, sine theta over there. So this is the full the full spherical coordinate system, and the Jacobian of this change of variable rho phi theta. After cancellation, it will be a 3×3 determinant, which we don't evaluate. Answer is just this. Okay, notice there's a phi here. Okay, there's no theta. Okay, they got cancelled away just like the polar coordinates. There's this phi here. Okay, the angle measured from the positive z-axis. So let's do an example. The volume of a ball with radius capital R, okay, and this is now 3. So if we want to calculate that, the integrand, this volume, is going to be the triple integral of the region E in the R3 space, which tells you where the points of the ball are. So I'll just skip the letter E and simply write you the equation. So the x, y, z is in R3 such that x squared plus y squared plus z squared is less than or equal to R squared. Okay. So this is the region that we want to integrate, and then dv. So this is a big long thing. So when you have this in the Cartesian coordinates, this is not very nice. So now we using the spherical coordinates. So this guy is your E. Your E is now just the region where you have these rho and phi and theta. Your rho will be from 0 to R. Your theta will be from, let me start with phi, the standard biggest range from 0 to pi, and the theta will be from 0 to 2 pi. Now this is what I wanted to say. This is A, this is B, this is C, this is D, this is E or F. These are constants. Okay, the previous example was not, but this one is a constant. So this is a good thing because when we get our triple integrated integral, the integration will be easy because of Fubini's theorem. We can separate it quite easily. You don't have to worry about the order. The next important guy to deal with is the dv. The dv has now a formula, so you need a multiplier. That multiplier is rho squared psi phi. And with this multiplier, the rest are just the variable names. You have d rho, and then d phi, and then d theta. So the Jacobian, the knowledge of this extra multiplier, tells you this extra information when you are using non-rectangular coordinates, and that's the main work of it. Okay? And so once you have that down, your v now it becomes a much easier integral. So integral is just going to be the integral. So let me start with the innermost. Let me start with let's r from 0 to r for the d rho. Okay, so 1 times, we have the d rho inside, and don't forget this, put it down there, rho square. Yeah, so the rho square psi phi, this is the star of this calculation. The next level, let me do d phi, it's from 0 to pi, not 2 pi, and the outermost is the theta from 0 to 2 pi. And now the integrand with this Jacobian is a product of functions in only one variables. So just like what we've done before, we can more or less separate them. Okay, so this would be the same as the product of 3 single integrals. So what we have here for the first integral is 2 pi. The second integral is going to be 2. Okay, and the last integral is going to be rho cubed over 3. It's going to be r cubed over 3. So multiply all these together, you get 4 pi over 3 r cubed, just like before, with way less effort, assuming you know this Jacobian. So once you know this Jacobian function, calculating volumes like this will be easy. Now the use of these change of variables paves the way for us to do some important integrals, and both in let's say other fields like probability, physics. I'll get you one example each. So let's do an example for polar coordinates. So this is an example. We want to integrate from minus infinity to positive infinity e to the power minus x squared dx. Well, this is a single integration, not double, not triple. Okay, and it's improper. Now this is something that is slightly tricky, but it's good to see this because it's one of the fundamental integrals when you're doing probability, and it's done by Gauss. So by definition, this integral, when it exists, should equal to the same thing as this. Okay, so in general, improper integral should be checked for existence when the a and b, the upper and lower, if the improper integral is checked for existence. Just like you're doing two variable limits. But once you have checked for its existence, then you can use the same number. It's the Cauchy predictable value. Okay, so that's another story. But I'm just focused on how we calculate that using the new trick we find. Okay, so once you have this idea, what we're going to do is a favorite trick that a physicist will also show you. Okay, so we would imagine that we have a fixed value of x in the integration process, and we consider exactly the same integral, but similarly in the y direction. Okay, it's a single integration. Okay, and instead of integrating from minus infinity to infinity, from minus a to a, you could look at this as integral from minus square root of a squared minus x squared, and that's a squared minus x squared e to the power minus y squared dy. So this looks like this. I'm doing an integration over a circle. So instead of doing a single integration, I'm doing a double integration over this upper half circle. We've done this before. And this is the lower half circle. Okay. So these are the upper and lower limits. And the long story short, so this is the justification of the improper integral. What we want to do is we do I squared. So instead of just doing a single integral, we make things harder, seemingly. So integrating from minus infinity to positive infinity, integrate this times that, and because we were some hand waving, we fix x so that we can make y depend on it. Okay? We know the number is going to be converging, so we're making a lot of geometrical arguments. And what I want to see is you get together there is a limit as a goes infinity of a combined integral. E power minus x squared and then e power minus y squared, and then dy dx. And if you use the substitution, which is a two-dimensional substitution, change your variable, then you will have a Jacobian. This part is dA. And dA will be replaced by r d theta. And this part minus the sum of x squared plus y squared will be replaced by minus r squared. So the long story short is you will become an integral like this. Limit from a becomes limit from r, that's going to infinity, and then you're integrating r from, let me call that big R, and then the r from 0 to capital R, and then you have this e power minus r squared r dr. And outer integrand is the full circle, 0 to 2 pi. And now this suddenly becomes integral because here you can use normal substitution, usual substitution. Use u equals r squared. Okay? So once you have this substitution, you see, okay, you can just actually get the antiderivative, which is just minus e power minus r squared over 2. Okay? And I plug in the upper and lower limits. Little r equals big R, little r equals small r. And the other one has nothing to do with r. You can just pull it to the front. And long story short, this guy, the front in front is 2 pi. The one behind is 1/2. And it gives you pi. And so, if your I is integral from minus infinity to positive infinity of e to the power minus x squared dx, where the integrand has no antiderivative. Okay? In this case, squaring it, when with the trick that I shown above, gives you pi. And so therefore, I, being positive, must be square root pi. And this is by Gauss. Very smart trick. So here's another example where these coordinate systems come to play. Let's look at the case where we have a solid and we want to find its mass. So here's an example with cylindrical coordinate, which is just the usual Cartesian coordinate for z, and then with xy replaced by r theta. So now I have a solid bounded by, so let me call it E, a solid E, bounded by these equations. You have a cylinder, and you also have a plane. So this is a cylinder because the Z is free, and you also have a plane. So this is a plane. And you also have a paraboloid, z equals 1 minus x squared minus y squared. So it looks something like this. So let me try my best to sketch. You have this x, y. Upper plane is easy to sketch. Okay, so first you sketch a cylinder. Cylinder has the projection being circles. So I have this cylinder. At this point, we have z equals 4. So I have a plane on the top ending. But below, we have something that's rather tricky. This extra weird thing that gives you some parabola that's upside down. So it might look like this. So it looks like if you have played badminton before, like the badminton shuttlecocks, the box looks like that. The bottom part is for the hollow between the feathers. So you put that on the bottom, but the top you have the usual lid. Okay, so we want to find the solid E's volume. And this volume, and not really. We now find the mass of it. Make it slightly harder. Okay, so suppose the mass of E depend on a non-constant density function, which I would write it as I don't use rho. Let me just use f of x, y, z, and the density, which is proportional to the distance from the z-axis. Okay? So you're going to be having the densest part inside and the less and less dense outside, perhaps, okay? Or the other way around. So even this function f could not be written in x, y, z with convenience unless you use square root of the distances from the z-axis, which is the xy coordinates, right? Square root of x squared plus y squared. A quick way is to choose cylindrical coordinates. And the cylindrical coordinate is nothing but keeping one of the coordinates and use polar coordinate for the rest. So what we'll do is we will use x equals a function of r theta, and this is r cosine theta. Y is a function of r theta, which is r sine theta. And z equals z, nothing changed. And let's write that in advance. The dv, which was original dx, dy, dz, you keep the dz, but the dx, dy will convert to dr, d theta with a Jacobian of r, just like before. So this is the new stuff from polar. Okay. So with this, I will also write, so let's rewrite the function. The f of x, y, z becomes f of r theta z as simply, let's say, k times r. Okay, because here the distance here is given more succinctly as just r if you take the square root of x squared plus y squared. So this is the constant of proportionality. And so what we're really trying here to do is your mass, which should be the triple integral over the region of your density function, and then dv, which would be dx, dy, dz if you don't choose a different coordinate. And now, in our case, will be just k times r. And then you have this r, dr, d theta, dz. Okay, so you get things easier for the element of integration and also the description of the density function. And this is our mass. And how about the range of integration? Yeah, the range of integration, you see that in the theta wise. So if you're rotating about the z-axis, that theta gives the angle, and you're doing full rotation. So theta here is nice, from 0 to 2 pi. Okay, and z is also easy. It's from the x, y plane all the way to the top plane, which is 4. And the last thing you need to figure out is let me see, not the bottom plane. This part's not right. The top plane is 4, but the bottom plane here, if you plug in the radial distance here, it should be 1 minus r squared. Okay, and here there's this 1 minus r squared here for this part. Let me use blue. This 1 minus r squared is for this guy. Okay, So the lower surface 1 minus r squared instead of 0. So if this, you have this, and finally you have the phi. That's not phi. The r, yes. So we are looking at the radius 1. So that's the easy part. I mix up. So I should put this here. Z is the last part. Okay. So this integral becomes, let me give myself more space to describe it. Integral 3 parts. The innermost part shouldn't be r because the z depends on it. So I should put the z as the innermost part, and then followed by dr, and then followed by d theta. D theta is the easier part. So the z should go from 1 minus r squared all the way to 4. Okay, so that's the innermost part. The middle part, the r goes from 0 to 1, and the last part, theta, goes from 0 to 2 pi. It is a solid revolution. Okay, so now I don't need the bracket to indicate the separation of them. I put a bracket here instead. So what we're doing here is just k times integral from 0 to 2 pi, integral from 0 to 1 of r squared dz dr d theta. So this is the z function, and this is the r function. This is the theta function. And in the iterated integral form, this is no longer hard to deal with. The answer will be k times 12 pi over 5. So the mass of that solid is this guy. Okay, so I'll stop here. We'll do more examples in the problem solving class.